Welcome to Microlecture 19, where I will start to use model kits to show you some conformational analysis tricks with propane and butane. Okay, so I have a molecular model here. Actually, I'm going to start with a simpler one. I'm going to start with ethane, so let me remove a carbon real quick. So this is a lot like the model kit that you might have available to you, but this one's bigger because I use it to teach with in the lecture hall. And it's not as easy to build with. So what we're going to be doing is looking at molecules and thinking about what happens when we rotate about carbon-carbon bonds. So here we're not talking about like constitutional isomers where we'd have to break bonds and reform them somewhere else if we were going from one isomer to another. These are conformational isomers. Conformational isomers are conformers of one another and only require something like a simple carbon-carbon bond rotation to get from one to another. And so we're thinking about what does this molecule look like most of the time. And there's lots of situations, especially the larger the molecule gets, you've got more bonds that you can rotate about. So let's take the simplest case scenario, that's ethane, so CH3 on this side, CH3 on this side. And first we're going to draw it out kind of in a way that takes a little bit more energy and is a little less intuitive, and thereby show you why the other way is better. So right now I have a hydrogen atom, a carbon, and then another hydrogen atom all in one plane. So I'm going to go ahead and draw that like this. And then I've got hydrogen atoms that are coming out of the plane. And then I've got hydrogen atoms that are going back into the plane, so behind the structure. And we're going to be talking about rotating about the carbon-carbon bond. So maybe I take that one that was in the same plane and I move it back. All right. So what I've done is I've rotated about this carbon-carbon bond, and I'm going to leave this side over here the same, and I'm going to show how this hydrogen is now in the back. Okay, and then we've got one pointed out at you, and then this one is in plane. Okay, so now the one that's in plane, we've got this bond and the middle bond right here and the bond up here all in one plane. Looks like a Z. All right, so that my whole point of doing that is that it's not really easy, and there's an easier way. And so to kind of track these interactions that happen between atoms and thereby trace kind of their energy and see what situation would be the lowest energy or most favorable, we're going to use Newman projections. So let's use the simplest molecule to kind of learn how to draw a Newman projection. A Newman projection is one in which you're looking at an atom that's like this carbon atom, for example, that has another atom directly behind it. Okay, so the other carbon atom is directly behind it, and the way we're going to draw this is we're going to have a circle. I'm going to draw a circle for the front carbon, and I'm going to show all three groups that are coming off of that front carbon. I've got a hydrogen that's pointed upward. Okay, and I've got a hydrogen that's to the left and a hydrogen to the right. And then immediately behind it, I've got a hydrogen atom. So I'm going to draw that by just off to the side of it. I've got another hydrogen atom and then another hydrogen atom. This is a Newman projection, and in this position, where all of the atoms are directly behind the other atoms, we call that eclipsing. It's a higher energy state for this molecule because we have something called a dihedral angle, which is between this hydrogen in the front and this hydrogen in the back. Okay, dihedral angles involve 4 atoms. 1, 2, 3, 4. Okay, so it's always adjacent, groups that are off of adjacent atoms. So these are the adjacent carbons. We're talking about the angle that's involving the groups that are coming off of those adjacent carbon atoms. In an eclipsing situation, that dihedral angle is 0 degrees, right? These two groups are pretty much right on top of each other. All right, so what happens when we rotate 60 degrees? I'm going to rotate the back carbon. So much better. So this is called a staggering position or staggered position. So I'm going to redraw everything from the front, okay, just exactly the same way. And in the back, now our bonds are looking more like this, staggered. And the dihedral angle here is 60 degrees. All right, so usually with Newman projections, we're rotating about the back carbon or the front, but I usually rotate just around the back by 60 degree increments. So staggered, eclipsed, staggered, eclipsed. All right, so we know the difference between staggered and eclipsed. We understand what a Newman projection is, and we've covered dihedral angles. And this one's pretty simple. It just kind of goes back and forth between eclipsing and staggered, and then we understand that the molecule would spend more of its time in this position, much more of its time, because this is a lower energy state, and it's just a better place for the molecule to be. So staggered is low energy, stable, and eclipsing is high energy, less stable. And it makes sense now too that this is the way that we draw our hydrocarbons, right? Alternating up, down, up, down, up, down, staggered. So the next one I wanted to cover is propane, and so I'm just going to remove a hydrogen atom here and put a methyl group in its place, and I will have propane. So 3 carbons in propane. And again, we're going to look down this carbon-carbon bond, so I'm still going to have 3 hydrogens in the front. And it's going to look very much like ethane, where we can have eclipsing interactions like this, and staggered, and eclipsing, and staggered. So let's draw the eclipsing one first. So I've got my front carbon with all 3 of them with hydrogens, and then a methyl group is eclipsing in the back. And then I've got my 2 hydrogens that are eclipsing back here. Okay. So these are the eclipsing hydrogens in the back. Okay, and so I'm going to rotate it 60 degrees, and I wanted to rotate all the way around. And so the way we're going to show that using our Newman projection, 60 degree rotation. Everything stays the same in the front. And there's our methyl group, our CH3 group right there. Okay. Now, here's the thing, is that now this group is a bit bigger. When we encounter the eclipsing position, okay, every other time we go around by 60 degrees, we're going to start having something called steric strain, because we've got these hydrogen atoms coming off back here. We've got the opportunity for 2 hydrogens to kind of get in each other's way. I realized that I lost a bond here at some point, so that hydrogen back on. And so because of that close proximity of these hydrogen atoms, they're kind of bumping into each other's electron clouds. The eclipsing is even more high energy than it was before, and it's because it has steric strain. That's this idea that electron clouds are bumping into one another, and it's between the H and the CH3 that are eclipsing. All right. So there's even more reason for this methyl group to be staggered with respect to the hydrogens in the front. So staggered. There's no steric strain, and it's a much lower energy. Okay, much more stable. So I want to take you next to butane. One more carbon added to the chain. And what we're going to do is view down the middle bond this time. So here's my butane, and I'm going to view down this middle bond right here. So this is my front carbon now. I have a methyl group in the front and a methyl group in the back, and I'm going to rotate the back around like so. So we're going to start with the two methyl groups very close to one another, and if I take it this way, we see how close those hydrogen atoms are going to get in the eclipsing position. So very, very high energy state. And so this is our first one that we're going to draw with our Newman projection. This time we're going to draw all of them, so I'm trying to draw small. Okay, and so I'm rotating 60 degrees, and that's going to get me to this position right here. So methyls are still kind of close. You see that? So whereas normally being in a staggered position is going to relieve the molecule of all of its types of strain, in this position we still have steric strain. Okay, so these methyls are still quite close to each other, and the hydrogen atoms on the methyls that are on adjacent carbons are bumping into each other. So the way we're going to draw this one, again, all hydrogens, let me fix that. It's not all hydrogens anymore. We have the methyl group in the front. Same as before, we had a methyl group, methyl group. So here we have eclipsing CH3, CH3. I don't think it can get any worse than that for that initial structure. We can't cause any more strain. We've got the eclipsing bond strain, and then we've also got a great deal of steric strain. So both of these are going to cause the energy to go sky high. Okay, so very high energy. And then in this next one, the second one here, we've relieved the strain a little bit, but the methyl groups are still 60 degrees away from one another. And so this is a new type of interaction we haven't talked about called gauche. So it's when two, substituents are staggered, but they're kind of as close together as they could possibly be without being eclipsed, 60 degrees away from each other. All right, so we've relieved the energy a little bit by forming this gauche interaction, but it's still somewhat high energy due to steric strain. So rotate by 60 degrees again. Leave everything the same in the front. CH3 is pointed up, 2H is pointed down. CH3 is eclipsing here. Okay, again, because of the eclipsing, we've got a great amount of strain. Here we're eclipsing CH3 and a hydrogen, and it's still steric strain. If you eclipse a methyl group with anything, you've got steric strain going on. All right, we're going to rotate one more time. Going to hold this in such a way that you can see. The methyls in this case are going to be as far away from each other as they can be. Let's draw that. All right, and then that's going to be the most ideal energetically, the lowest energy possible. And then we're going to move the methyl group to the left-hand side. And so we're back to a high energy eclipsing position. Okay. One more 60-degree turn, and we see that we're back to being staggered, but it's another gauche interaction. Okay, just on the opposite side. So let's draw that one. And then if we rotate one more time, we get back to our original structure. So these are all of them. And it turns out you can map the energies of each of these. Let's kind of do that in the upper right-hand corner. We can think about each of these rotations. So the first 60 degrees, 120 degrees, okay, and then we just won't show the 360, which is going to be the same as the original position. So on the y-axis we have energy, and so we're starting back out at the very beginning. Okay, so we haven't rotated 60 degrees yet, and this is the highest energy state that it possibly can be. So we're going to put our energy way up there, and then we're going to rotate 60 degrees and come down in energy quite a bit, but not as much as we could because of that gauche interaction. Okay, and then rotate 120, and we get a high energy state, but it's not as bad as it was before. Okay, because before we had eclipsing CH3s, and over here we have eclipsing hydrogen and CH3. So it's not quite as high in energy. So far the curve looks kind of like this. And then at 180 degrees, we've got our lowest energy possible state. This is where the methyl groups are kind of as far away from each other as possible. And so when we're at 240, we're actually at a very high energy state. We're eclipsing again. And so that's going to go back up in energy. and then we come back down to a gauche position. If we were to go the full 360, we would go right back up to where we started with.